So I want to talk about some projections for the future of coral range expansion under future climate change. So this image here is going to be familiar to most of you here. So as we know, increasingly driven by anthropogenic climate change, our coral reefs are degrading around the world. And we're expecting that to continue and probably accelerate in the future under future warming. On the other hand, as the oceans warm and waters that were previously too cold to be habitable for coral reefs become warmer, we can ask the question of whether we should start to expect coral reef formation to start occurring in new high-latitude environments. And obviously, this kind of hypothetical situation is not going to do anything about the devastating impacts of the potential degradation of our present-day tropical coral reefs. But if high-latitude seas do start acting as refugia for tropical coral species, that could at least act as a buffer of biodiversity, of coral biodiversity, and mitigate the risk of large-scale coral extinctions in the face of climate change. There are several kind of observational reasons why we might expect there to be range expansion of corals. So first of all, from the geological and paleontological record, we know that when the Earth was warmer in the past, tropical coral reefs were found at higher latitudes than they're found in the present day. So this mechanism definitely has taken place in the past, and over the past few decades, in some places in the world, people have been observing or noting new tropical coral species appearing in sites where they've not been observed before. So that's not the case everywhere. There are plenty of places where there is no evidence of coral tropicalization, but at least in some places, there does appear to be colonization from new tropical coral species. So if we want to project the potential for coral range expansion into the future, one approach you could take is using a statistical species distribution model. One of the big limitations of these models is that they assume that the corals are in equilibrium with their environment. And for corals, which are relatively slow growing and also rely on passive dispersal to move to new environments, that's definitely not going to be a reasonable approximation for them. So we've been working on this eco-evolutionary model called Ceres, which is a global model, 8-kilometer resolution. And rather than modeling individual coral species, we first of all distinguish between what we're calling reefal coral assemblages. So these are the kind of diverse coral assemblages we typically find in modern coral reefs, and contrasting that to non-reefal assemblages, which are the much lower diversity coral assemblages we find outside of the main zones of reef formation. And we're also considering a competitive life history strategy. So these are, for example, most acroporid corals. They tend to grow really quickly, but also undergo more mortality during acute heat stress. And then we have this stress tolerant strategy. So these are like many Porites corals, for example, follow this strategy. They tend to be more slow growing, but also appear to be more resilient in response to marine heat waves, for example. So we're considering these 4 hypothetical coral assemblages, and we assume that coral growth rate depends on temperature, pH, light intensity, available habitat, and competition. We allow the coral thermal optima to evolve through time based on selective pressure and immigration, and we use demographic connectivity data from a global larval dispersal simulation. So based on that's the model framework, and this schematic here summarizes the experiments we've been running using that model. So we start off with a 5,000-year spin-up period to allow our virtual simulated corals to reach a pre-industrial equilibrium. And we then follow that with historical climate forcing from 12 different CIMAR-6 models. And then after that, we impose future climate projections from 3 different emission scenarios. Again, each of those using 12 different CIMAR-6 models for a total of 36 different simulations. And then from the end of the current century, for another 1,400 years, we keep climate fixed at the 2100 values to look at how the distribution of corals might equilibrate after this 21st century climatic shock. Looking at some of the results, so this graph here, on the y-axis, we have the simulated global total coral area. X-axis, we have time. And the key line to focus on here is the orange line, which is for our reefal corals, so our corals that are growing in our simulated coral reef assemblages. And unsurprisingly, the model predicts a significant decline in reef or coral cover by the end of the current century. There's quite a lot of variability across, depending on which particular climate model you're using as the input. But on average, the model predicts a decline of roughly 70% across reef or corals, which is a bit more optimistic than some previous models, but still pretty dire, obviously. There is quite a bit of difference between different future emission scenarios. So, for example, this main line here, this sort of line is for the kind of middle of the road SSP 4.5 scenario. If you are an optimist, maybe we might follow something more similar to this dashed line, but that's looking increasingly unlikely. If we look beyond the end of the current century, the model does predict a recovery of coral cover. But the important thing to note here is that the left-hand side of this graph covers a timescale of 80 years, whereas the right-hand side of the graph covers 1,400 years. So although this recovery looks pretty dramatic in this figure, it's actually taking place over centennial timescales, so a very, very slow recovery. And then looking at the simulated geographic trends, here we're looking at the relative percentage change in coral cover at the end of the current century compared to the start of the current century. Reds are reductions in coral cover and blues are increases in coral cover. So blues are cases where we'd be expecting or potentially projecting range expansion. And as you can see, there's not very much blue. So the model predicts on the order of a few tens of kilometres squared of new reef or coral cover, primarily in Australia, and to a lesser extent north of the Florida Reef Tract. But this tens of kilometres squared of new reef or coral cover is more than 3 orders of magnitude less than the expected decline. So, pretty much the model predicts negligible or very, very little range expansion. And if we look further into the future, over 1,000 years into the future, now we do potentially have genuine range expansion. So centuries into the future, it is looking very likely, and that's kind of supported by geological evidence, that we may have proper tropical-esque coral reefs forming beyond their current range distribution in Australia, some places in the US, potentially some places in Japan. But again, these are predictions for the very, very distant future, and it's not going to help us when our coral reefs are facing a very acute crisis over the next few decades. So one of the other benefits of using a process-based mechanistic model rather than a statistical model is that we can try to investigate what are the processes that are limiting the rate of range expansion. At least in this modelling framework, there are 2 processes that appear to be kind of restricting this rate. First of all, the relatively slow growth rate of coral populations at their kind of range limits. And secondly, the coral genetic variance, which affects how quickly corals can adapt evolutionarily to new conditions. And what is interesting is that the model suggests that dispersal limitation, or dispersal, is probably not, or is potentially not actually limiting the rate of range expansion. It's probably these 2 processes that are limiting how quickly corals can colonize new communities. So, as I mentioned, we're modelling these 2 different life history strategies, this competitive strategy, which is predominantly branching corals, and this stress-tolerant strategy. And in the short term, and kind of in line with observations, the model predicts that these competitive corals are going to be disproportionately impacted by acute heat stress because they tend to undergo more mortality after marine heat waves, for example. But what's quite interesting is that the simulation suggests that this move towards stress-tolerant community compositions might be transient, because after the end of the peak rates of warming, the model predicts a really strong rebound, which is kind of shown by this green colour here, a really strong rebound towards competitive life history strategies, which then maintain dominance over coral reefs for hundreds of years into the future. And in the model, that happens because these competitive corals are really effective at recolonizing degraded reef habitat once conditions have returned to conditions that are kind of conducive towards their survival. So in the short term, we're probably going to see a continuation of what we're seeing already, but it could be, and this is kind of probably more of academic interest, but it could be that in the long-term interest of this kind of acute heat stress in coral communities could be a shift towards, or kind of a longer-term shift towards competitive strategies. So obviously, this is a model. There are many sources of uncertainty, and I've listed a bunch of those potential sources of uncertainty on the board here. And considering these uncertainties are really important for kind of interpreting these results. First of all, the model assumptions are generally favourable for range expansion. So for example, in the model, we assume that all habitat shallower than 20 metres is potentially habitable for corals, which is obviously not true. That's a really, really optimistic assumption. So if anything, our model is probably going to be overestimating the rate of range expansion, not underestimating it. And that's why I feel relatively confident in our conclusion that we're probably not going to see significant expansion of our coral reefs in new higher latitude environments this century. And then before I finish, I just wanted to show one graph that is not one of my results, but I think it's quite interesting. So here we're looking at some geological results. So we have on the x-axis time going in millions of years. And in red, we have the reconstructed global coral reef volume. And as you can see, there have been times in the Earth's history before, like here during the Paleocene-Eocene thermal maximum, where there was a massive global reduction in reef volume. But then when you look at the paleontological record and you look at the diversity of coral taxa that are represented in the paleontological record, in some of these past coral reef crises, you find almost no loss of diversity. So in Earth's history, it does appear to be the case that coral reef crises are not necessarily accompanied by massive coral extinctions. Now, there are several ways of interpreting these data, and this is definitely not proof that we're not going to see large-scale coral extinctions this century. But I don't often see this paleontological data discussed, and I think it's quite interesting to consider when thinking about the future of our coral reefs. So the main conclusion, I think, from this modelling exercise is that coral reef range expansion probably is going to happen, but it's probably not going to happen anywhere quickly enough or anywhere near fast enough for it to really help buffer coral diversity against the stresses that they're going to be facing this century. And if you want to know more details, I can answer questions now, or we also have a preprint here that you can have a read of.